Section 5.3 in Lay's linear algebra, which is section 6.2 in Larson's. It's called diagonalization. Let's recall what a diagonal matrix is. Diagonal matrix is denoted by D. It's a square matrix, which a matrix that has all off-diagonal elements equal to 0. And this is the notation we use for diagonal matrix. For instance, if a diagonal matrix has its main diagonal elements as 1, 2, 0, 3, then the matrix is going to be what? A 4 by 4 matrix, okay, whose main diagonal elements happens to be those numbers, and off main diagonal elements are 0. Do you see it? So that's called diagonal elements. So the question is, how is this related to similar matrices? Well, we know A is similar to B. They have the same eigenvalues, correct? Remember, the relationship B is equal to S inverse times A times S. S is an invertible matrix. Furthermore, the simplest matrix that has these eigenvalues is the diagonal matrix, whose main diagonal elements happens to be what? The eigenvalues of matrix A. Consequently, the simplest possible structure for this product is the diagonal elements. In other words, we're trying to show that what? This guy is similar to the diagonal elements. Consequently, that would be the same as showing what? A is similar to a diagonal matrix. So the question is, given an n by n matrix, when does an invertible matrix S exist such that S inverse times A times S is the same as diagonal matrix whose main diagonal elements happens to be the eigenvalues of matrix A? In other words, when do we say a matrix is similar to a diagonal matrix? And once again, diagonal matrix is a square matrix whose main diagonal elements happens to be, in this context, eigenvalues of matrix A, and off main diagonal elements happens to be 0. So with that said, the answer is the following. A square matrix is similar to a diagonal matrix if and only if it's non-defective matrix. What was the non-defective matrix? In other words, if you had n by n matrix, then you had to have n many linearly independent eigenvectors. In other words, you had to have a complete set of what? Eigenvectors for the matrix A. So what it amounts to is a matrix is said to be diagonizable if it is non-defective. And what is non-defective? If it has complete set of what? Linearly independent eigenvectors. So if the dimension of the matrix is n by n, so you gotta have n many linearly independent eigenvectors. So the number of vectors here gotta match what? The dimension of the matrix A, and they all have to be linearly independent. So they have to form a basis. So this guy, S inverse times A times S, is equal to diagonal matrix, where lambdas are eigenvalues of A, not necessarily distinct corresponding to what? V1, V2, Vn. So they don't have to be necessarily distinct. So here's an example. Suppose you have a matrix A, 2 by 2, correct? And you found the corresponding eigenvalues, namely 5 and -1. So now you have to find the corresponding eigenvectors for each of these eigenvalues. If lambda is equal to 5, the corresponding eigenvector is 1, -3. If lambda is equal to -1, the corresponding eigenvector to lambda is equal to -1 is 2, -3. So in this section, we will see what that mysterious invertible matrix S is. Turns out it is just what? A matrix which contains what? Linearly independent eigenvectors of matrix A. Notice this is V1 and that's V2, so that's S. So S is a vector whose columns are what? Linearly independent eigenvectors of the given matrix. This you gotta find. Once you get your hands of S, then you gotta find its inverse. So this is inverse of S. Then you multiply inverse of S by the matrix according to this times what? S itself. Lo and behold, you get this 2 by 2, which is a diagonal matrix. But notice the main diagonal elements happens to be the same as what? Eigenvalues of the original matrix. Do you see it? Conclusion of the problem, A is similar to what? To diagonal matrix. Why is it similar to diagonal matrix? Because we had what? Two linearly independent eigenvectors for a 2 by 2 matrix. So therefore matrix A, okay, these are linearly independent, correct? Independent what? Eigenvectors. Therefore, the conclusion is, look, A is a non-defective matrix because it has complete set of its linearly eigenvectors, correct? Therefore, S exists, and S is a matrix, square matrix, of course, whose columns happens to be the eigenvectors of matrix A. Then we gotta find S inverse. Then when we form this product, lo and behold, we should get a diagonal matrix whose main diagonal elements happens to be the eigenvalues of the original matrix, what? A. So the conclusion is we say A is similar to the diagonal matrix. Okay. So here is a definition of diagonalizable matrix. If A is similar to a diagonal matrix, then it's said to be diagonalizable. So if A is similar to a diagonal matrix, then it's said to be diagonalizable. Diagonalizable is synonymous to what? Non-defective. And non-defective is like what? The matrix has a complete set of linearly independent eigenvectors. In other words, you have just as many linearly eigenvectors as the dimension of the matrix. For instance, let's say you have a 3 by 3 matrix, and you like to verify A is diagonalizable. So what you have to do is find a matrix S that satisfies this equation. Sometimes all they want you to do is find that matrix S and stop. But let's see, how would you do this? Suppose you, from previous sections, you find the eigenvalues for this matrix as being what? 4, 4, 3. In other words, you have 3 eigenvalues, but the first 2, they look alike, so that would be 4 with multiplicity 2, and 3 with multiplicity 1. Remember, multiplicity of eigen values are called what? Algebraic multiplicity. However, if these guys repeat themselves, those are called geometric multiplicity. Anyways, if lambda 1 and 2 equals 4, because they both happen to be equal, you get 2 linearly independent eigenvectors. Because the reason I got 2, because I had 2 free variables. When you substitute lambda is equal to 3, you get one linearly independent eigenvalues. So you have a complete set of what? Eigenvalues. Linearly independent eigenvectors. Therefore, these guys form a basis for R3. Therefore, A is defective matrix. Therefore, it's diagonalizable. So, diagonalization is directly related to whether or not the matrix is non-defective. If a matrix, square matrix, is non-defective, then it's diagonalizable. What does that mean? That means you can prove the matrix is similar to a diagonal matrix. So in this case, you can find that mysterious, square matrix S. How do you construct S? You just what? List the linearly independent eigenvectors for matrix A in each column of matrix S, just like so. V1, V2, V3, V1, V2, V3. There they are. Now, we gotta what? Form this guy, which you really don't have to because the question was just find vector matrix S, and we did. But the fact is, if Rn has a basis of eigenvectors of A, then A is diagonalizable, which that turn, gets back to saying that A is non-defective. So what I'm saying is, if you find the inverse and multiply it by matrix A and multiply that mysterious matrix C, it's supposed to be similar to what? Diagonal matrix, whose what? Main diagonal elements happens to be lambda 1, lambda 2, lambda 3, because I listed what? The columns of S in terms of V1, V2, V3. So what does that mean? That means the ordering of eigenvalues in the diagonal matrix must be in correspondence with the ordering of the eigenvectors in matrix S. What does that mean? That means suppose instead of listing the linearly independent eigenvectors for A, you decided to list them as V1, V3, V2. Therefore, S inverse times A times S, which is equal to what? Diagonal matrix. Inside the parentheses, notice the order matters here. Now you got to go lambda 1, lambda 3, lambda 2, because you went V1, V3, V2. So here, the diagonal matrix, the order of diagonal matrix should be lambda 1, lambda 3, lambda 2. In other words, your diagonal matrix is this, 4, 3, 4. Everywhere else, you have to have what? 0. So that will be a 3 by 3 matrix, correct? Whose main diagonal elements are eigenvalues, but the way you list the eigenvalues depends on how did you list the what? Eigenvectors in matrix S. So what would be the application of a matrix which is diagonalizable? Well, turns out if you raise a diagonal matrix to any power, all you have to do is what? Raise those eigenvalues to that power, because everything else is 0. So if you have a matrix which is non-defective matrix, so it is diagonalizable, so that means it's similar to what? So this implies this is the same as saying A is similar to a diagonal matrix. Okay, if that's the case, then from this equation, if you multiply both sides of this equation by S, the left multiplication, you get this, because S times S inverse is identity matrix times any matrix is the matrix itself. At this point, you would multiply what? Both sides of this equation, right multiplication by S inverse. Then S times S inverse is identity. So on the left side, you get A. On the right side, you get SDSI. Now, suppose I raise A to the power of 2. That will be A times A, which is SD S inverse times itself twice. But remember, S inverse times S is identity. So these guys disappear. All you get is what? Is SDD what? S inverse, which is S d square S inverse. So in general, if you raise a matrix, which is similar to a diagonal matrix, all you have to do is form this product and just raise what? The diagonal matrix to whatever the power you're raising the A to. And SS and S inverse are pretty much the same matrices which we have found previously. Okay, so here is an example. Um, the question is, verify this guy is diagonizable and find the matrix S such that this is true. Okay, so you do the usual steps to find the characteristic polynomial. You set it equal to 0 to find the eigenvalues for matrix A. For each eigenvalue, you find the corresponding eigenvector. So in this case, I came up with 1, 3, and 1, 1. So therefore, the matrix S contains of what? The columns of matrix S contains of those two linearly independent eigenvectors, namely V1 and V2. Then I have to find S inverse. Once I get my hands on S, I have to find S inverse. And then I have to what? Form this product. When I do, I will end up with this matrix, which is a diagonal matrix. But the beauty of it is the main diagonal element happens to be the what? Eigenvalues of the original matrix. Do you see it? The conclusion of the problem is what? A is what? Similar to the diagonal matrix. So therefore we say A is diagonizable. So a matrix is said to be diagonizable if it is similar to a diagonal matrix whose main diagonal elements happens to be the eigenvalues of the matrix A. So application, which we just mentioned like a few minutes ago, is right here in this example. So you can see the application. Suppose you have a 2 by 2 matrix and you were asked raise that matrix to the power of 3. Instead of multiplying this guy by 3, what you could have done is find the eigenvalues and the corresponding eigenvectors so you can form the matrix S. Okay. Then what? Then you would use the formula that what? A cube is equal to S d cubed times S inverse. Keep in mind the diagonal matrix in this particular case is what? A 2 by 2 matrix, which its main diagonal elements happens to be the eigen values of the matrix A. Remember, you cannot do this for every matrix, every square matrix. It has to be diagonizable, meaning it has to have what? Complete set of what? Linearly independent what? Eigenvectors. So in other words, it has to be non-defective in order for it to be similar to a diagonal matrix. Once you made sure it's diagonizable, then you can use that formula. In this case, if you raise a to the power of 3, that's just like what? Multiplying s by d cubed s inverse. If this is d, all you have to do is what? Raise the main diagonal elements to the power of 3. S pretty much stays the same, but S inverse, I need to find it, correct? I need to find the S inverse. When I do, here is A cube. So if you multiply this matrix by itself 3 times, we should get negative 127, negative 84, 378, and 51. And that's a beautiful what? Application, one of many applications of what? Diagonalization. In other words, a diagonal matrix. In other words, a matrix is called diagonizable if it is similar to a diagonal matrix, which a matrix what? Whose diagonal elements happens to be the eigenvalues of the matrix. Thank you.